So maybe just before we start, sorry, Winston, just a second. So probably some of you, or maybe all of you, will have gotten an email from the Isaac Newton Institute, or maybe even more than one email, asking for feedback and stuff. You will have seen probably that this email is a bit specific to a program in Cambridge, right? There might be questions there relating to accommodation in Cambridge and stuff. This has to do with the fact that we are the first satellite program and they are still adapting to that. I think what we should do is that we make a good faith effort to provide them with useful feedback about this program. And I am asking you to do that, please, because they are funding this whole program. We get a lot of money from them. And I think we had a good workshop, at least I think that. And they are doing this as a service to the community, keeping the community healthy. So I think as a service to them, we can try to give them useful feedback. Okay, so please remember answering this. Maybe we are not able to answer all the questions. Okay, I see that, but yeah. Okay, so hand over to Vincent.
Great. Welcome everybody to the morning session. It's a really great pleasure to introduce our first speaker for the workshop today. It's Crisan. We'll be talking about particle filters, nudging, and application to data simulation.
Right. Thank you very much. And it's great to be here. My thanks to the organizers for the invite to give a talk here. And I'm sorry I couldn't be here for the entire program and for the other workshop. Reading is a great place, and it's a favorite place of mine. It's my home away from home, and I hope that it will continue to be like that for many years to come. What I plan to do today, I try to make this a talk as applied as possible, and I'm going to bank on the fact that you attended Nicholas Kanta's talk yesterday, because he presented particle filters in some details, and I'll try to be quite brief on the background and sort of simply try to explain to you one of the many add-on procedures that we use in order to make the particle filters amenable to their applications to data assimilation. The motivation for this work that I've been doing for many years now, and we continue to do so, is that we want to apply particle filters to solve high-dimensional nonlinear problems, such as those that are encountered in data assimilation for geophysical fluid dynamics model. And so what I plan to do, I'm going to plan to sort of show you quickly how you can recast these data assimilation ideas into the context of stochastic filtering. I'm coming from stochastic filtering from a more theoretical background. And then I'm going to just briefly show you a page about particle filters. I'm hoping that you recall what Nicholas presented yesterday. And then I'm going to say what is specific to the particle filters, to this particular version of particle filters. And in particular, what we do here, we implemented 4 different additional procedures to the classical particle filter so that it works in for a state space that is of the order 10 to the power 6. Right, so 10 to the power 6. Of course, somebody has their mic on. Maybe you can mute them because I can hear them. So you know, people from the Met Office are in the audience, and the roughly something like a regional model. What I'll do, I'll just present roughly this notion of nudging. This is the thing that we studied in this particular work, and then I'll go on and show you how nudging works for a particular model.
First, okay, I apologize if I said this clearly. I am not saying that the response making is correct, but a lot of students it's so simple, it doesn't really close the last step. And rules out this interesting picture.
Shevchenko from Imperial College. In the earlier work, part of the other work is part of something that has been done for a couple of years and is published in 2020, and is joint work with Colin Cotter, Dario Holm, and Wei Pan and Igor as well. Okay, so let me start. I don't want to sell data assimilation to you because everybody is doing data assimilation. So I'm just going to show you a page to just prove to you that I know what data assimilation is. So the only point that I need to make here is that particle filters, the type of methodologies that I will present next, can be categorized, can be classified as sequential data assimilation. In other words, you have a set of model trajectories or possible scenarios. So I have to adapt my language depending on which audience I speak to, that are intermittently from time to time corrected, updated according to the stream of oncoming data. And then you can use this set of trajectories to infer information about the system, either current information, past information, or do forecast. So what I want to do, just gonna show you that essentially data assimilation is sort of applied part of a stochastic filtering problem, and it's really using stochastic filtering it's a very natural language to interpret data assimilation result, and stochastic filtering can provide a lot of numerical methodologies and new ideas into data assimilation. So what you have there, the model, your model in data assimilation is called in filtering a signal, or the hidden component if you talk about hidden Markov models. And this is usually a Markov chain, is modeled as a Markov chain. So because it's a model as a Markov chain, if you work with it in discrete time, then you have a transition kernel KT. And a simple example, a simple one-dimensional example of a Markov chain, you can think of a sort of a time series. Xt is a function of xt minus 1 plus another function of xt minus 1 times some noise. For example, a one-dimensional Brownian motion. This is a simplest possible way in order to visualize a Markov chain. And then you have an observation process. So the observation process is typically a function of the signal. It could be a noisy function of the signal, but in its most abstract form, the observation process is characterized by the likelihood function. So for each value of the observation, you're given GT. GT is the likelihood function that gives you how likely that observation is given the position of the signal, given an arbitrary position of the signal. So this is GT. So the two ingredients that are used to construct a filtering problem are the likelihood function, the transition kernel, and the initial distribution of the signal. And an example of an observation is, as I said, the observation can be a function of the signal plus noise, for example, a normal Brownian, normal random variable. Okay, so what you want to do, you want to compute the conditional distribution of the signal given the observation. So this is a probability distribution, right? So this probability distribution in discrete time satisfies a very simple transformation, a very simple recurrence formula to go from pi t minus 1, so the conditional distribution at time t minus 1 to the conditional distribution at time t, right? You go in two steps. So people that do data assimilations will recognize this immediately. The first step is the forecast step, where you just use the transition kernel of the signal to move forward the distribution, right? So this is a linear step. You use the model to move forward the conditional distribution. And the second step is the analysis steps or the update steps, the assimilation steps, where you multiply by the likelihood of the observation, and then you normalize to obtain, a distribution, a probability distribution. So that's the simplest possible way to show how you evolve this conditional distribution. Unfortunately, no matter how simple it is, you cannot compute this explicitly. You cannot compute this transformation explicitly unless you have a very specific forms, unless you are in the Gaussian case, for example, the linear Kalman filter. So I'm showing you here the classical particle filter. I'm not going to go through it. All I'm going to say to you is that the classical particle filter essentially follows these two steps, faithfully these two steps, by sampling, by doing some Monte Carlo sampling from the various distribution. Now, the point which is very important here is that no matter what the problem is, this particle filter is asymptotically consistent. In other words, as you increase the number of particles, you end up in the limit with the actual conditional distribution of the signal. So this says that you are on the right track. Of course, we will never in practice will think of using millions of particles to get there, but at least you do something that asymptotically will have no bias. Now, this is a great thing, and this can be applied, and people apply it all over the world, right? And it has a lot of success, particularly in low-dimensional problems. However, in high-dimensional problem, and this is the case of the data assimilation methodologies, the data assimilation application, it's not possible to apply it in that form, right? So you have to use additional methodologies to make it amenable to be applied for high-dimensional problems. So this is the case when the likelihood function has a very small support, one is in the tail for rare simulations events, rare events, and so on. There's many cases where you cannot just use the classical particle filter. However, you can use that as a template to produce an asymptotically consistent approximation of the conditional distribution of the signal. So in what I'm going to show you next, we use 4 different add-ons procedures, right? The initial system, and I'm going to show you the model in a minute, the initial system had 10 to the power 6 dimensions. And the first thing that we did, we reduced that from 10 to the power 6 to 10 to the power 4. So this was a model reduction. This was a model reduction method that we used, which was based on work from geometric mechanics developed by my colleague at Imperial, Daryl Hall. Then we had 3 additional procedures. We replaced the forecast step. We replaced the prediction step with a nudging step. And this is the purpose of my talk. I'm going to explain how we did this nudging. This is not the only type of nudging that you probably have seen. But this particular nudging, we use rigorous justification for this particular nudging. And then the assimilation step, we complement it with 2 other different procedures. One is adaptive tempering and one is jittering. And unfortunately, I can't explain that to you because I've only been given 20 minutes. So the only thing that I will explain will be the nudging procedure. So I'm saying in here, the nudging is you correct the motion of the particles. So you no longer evolve the motion of the particles according to the transition kernel of the signal. Then we have a model reduction and the tempering and jittering, which are additional methodologies to ensure that you can apply the method, the particle filter in high dimensions. Okay, so yes.
So I can't explain the particle filter. I think the second step is the step that corrects somehow your right?
Yes.
So why so this means that you are trying to correct it before?
No. So this correction step, the way you see this correction step in here, this is done in one go for the classical particle filter, right? So in general, what's going to happen is this G here is going to be very steep, right? So that means that two bad things can happen. One is all the particles end up in the tail of the G, which means that they will not describe the posterior distribution. They will only describe the tail of the posterior distribution. That the second thing will be, maybe you get lucky and you get one of these particles in the right place. That means that by doing this correction, you move all the particles in this position and you lose, then the sample becomes degenerate. So what you do, you need to do the same thing, but in more than one step. But this is what tempering and jittering does. You gradually bring the particles in the right place, not in one go. That's the correction. Okay, so nudging. So what do we do? As I said, initially, this term is not there. Initially, we evolve the system according to the kernel, the transition kernel of the signal. And then we say, no, We don't want to do that because actually we want to arrive in a region which is given by this transition, by this likelihood function. Let's try and find a way to move the particles in the right place, right? So what we do here, we add a term in here, right, which depends on the position of the signal at time t-1, but it also depends on the new data, right? So now we blur this thing about using the data only in the assimilation step. We move the data and use the data in the first step as well, in the prediction step as well. Why? Because we have knowledge. We receive the data. Why should we throw the particles wherever they want? We should put the particles in a way which takes into account the new data. And this is what nudging does. Now, we also want to be consistent. Now, if you have this term in there, of course, you perturb the law of the signal, right? So you have to do a correction of the law of the signal, and you'll do this correction of the law of the signal at the next step. And the resulting algorithm is going to be that this algorithm too will be asymptotically consistent. So you do not introduce a bias via this nudging procedure. Okay, so now I'm going to go, yeah. Remember, I only have 20 minutes, and I had the chair in here. We're going to stand up and say, you have only 2 minutes left. Go. No, ask me now.
So when you do the correction with F, now you have to choose for F very specific.
Oh, yes, and I'm going to tell you how I'm doing it. Yes, it's not just any F. All right, so the next thing that I'm going to do, I'm going to show you an example. So I'm doing the nudging for this particular example, right? This example is a solution of a two-layer deterministic QG quasi-geostrophic equation for the potential velocity, right? So I'm going to show you, there's going to be two layers. So think the oceans, and you take two slices through the oceans, the upper slice and the bottom slice, right? And then you'll see the vorticity evolving in these two slices, right? And the two slices interact with each other, right? And the bottom slice interacts with the bottom of the ocean, right? So this is the equation. I'll just show you the equation. There's not more time to go through it. And I'm just going to now show you the simulation. So here's the first one. See? Ready? Right, so this is the one that has 10 to the power 6 degrees of freedom. This is what it is. So we have two channels, right? We have periodic boundary condition east-west, and you have Dirichlet boundary conditions north-south, right? So the water goes this way, and you can see what you can see here. You see the vorticity. So if it's white, it means vorticity is 0. If it's red, it goes this way, faster and faster. If it's blue, it goes the other way. The one of the bottom, the layer of the bottom, there's less energy in there. Why is that? Because there's more friction. There's more friction. So and the two layer, they interact with each other, right? So this one here, you can see here, the mesh is 2049 by 1025. So this is the signal, is the discretization. I'll show you in a minute. Right? It's periodic here, and I'll show you the boundary condition on the page, right? So this is what we observe, right? We're going to we call them weather station. We're going to choose some values from the grid, 32 on the top, 32 on the bottom, and this is what we're going to observe, okay? So let me go back to my talk. Boundary condition, south and north, U is equal to 0. Dirichlet condition. Okay, and this is the interaction between the two. Okay, now the first thing is we cannot work with 2 million points, so we're gonna 2 million degrees of freedom. So we're gonna reduce the grid to something which is much more amenable. Now, when you reduce the grid, obviously now you're gonna ignore some of the subscales inferences, some of the subscales influences, and in order to account for those, we're going to add a stochastic term in the advection part of the equation, right? So why is that? Well, there's a whole theory about this, and I invite you to look at the paper and see where it comes from. is from geometric mechanics. What you want to do, you want the resulting model to still behave like a fluid. You want it to satisfy the curvature separation theorem. You want the particles of fluid to still move like normal fluid. Okay, so that's why you add this stochastic term. The stochastic term is going to be, you have to calibrate it. It's a sum of Stratonovich integral. So you have to calibrate it. You use the principal component analysis. You have to find out exactly how many sources of noise you need, and also the amplitude of the noise. It's not trivial. It's not trivial. It takes about half a year to try to do this precisely, exactly, right? So you don't just add any stochasticity there. It's not going to work. So you have to be very careful. The model reduction is essential for the success of the particle filter. Okay, so now we can work with the particles on a much more amenable scale, right? This is the scale, still about 10,000 degrees of freedom, and then which you can observe. So what do you observe? As I said, you observe for each of the two layers, you choose an 8x4 grid or 16x4 grid, and you observe the velocity at that point. That's your observation, the velocity of that point. So out of 2 million degrees of freedom, you observe at most 128 degrees of freedom, okay? With noise, so that everything is kosher, so that everything satisfies the precepts of stochastic filtering theory. Okay, now, for each of these things, for particles, you have to compute that likelihood function. You have to compute the weight, because that likelihood function is used to compute the weight. And this is how the likelihood function looks like, right? It's an exponential of minus. I'm sure you recognize this. You project the signal onto the observation grid. You take the difference between the observation and take the L2 norm of that, and you get what you want. Okay, now, heuristically, the closer your observation is to your signal is to the observation, the smaller, the smaller this is. That means that the exponential itself will be higher. The highest that it can be is 1, right? So what you do here, in order to try to assess the quality of your sample, you compute something which is called the effective sample size, right? Which is the inverse of the sum of the normalized likelihood. Now, the point of this is that the higher these likelihoods are going to be, if they are all 1, in some sense, my sample is perfect, okay? But they will never be 1. Most of the time they will be very small. It's going to be 1 which is going to be very big. So what you want to do, and this is what nudging is trying to do, is trying to raise these likelihoods, make all these likelihoods, these weights, as high as possible, right? So what you do, we add a drift term. So this was the term that's coming from the fact that I reduced the model, and I'm adding here another deterministic term in here, which for those of you that heard about Gilsano's theorem is there, and is chosen like that because that means that the law of the new process is absolutely continuous with respect to the law of the old process, and you can find out what is the radon-Nikodym of one respect to each other, so that you put it in the likelihood. So when you compute the new likelihood, they look like this. Okay, this is ugly. You can simplify it, and eventually, okay, so what you want to do, we want to maximize this likelihood, which means that you want to minimize what's inside, right? Now, this is what I'm writing in here. You minimize what's inside, and you want to find these lambdas in there, which are the new degrees in freedom, so that this gets minimized, right? And, there's some mathematics to be done in there. Eventually, you find out that you cannot do it perfectly because you have these increments of Brownian motion. Yes, I know, just give me a few more minutes. And okay, and then you eventually, after you do a conditional expectation of this quantity, is just a quadratic optimization problem. So you can compute these lambdas explicitly. You plug them in there, and this is going to give you the nudge system. Okay, and everything is rigorous, and everything is computable. And as I'm saying here, this is still remain asymptotically consistent. So I'm going to show you now first the twin experiment. The twin experiment is when I work with a signal that is not the original signal, but one which is just a realization of the SPD itself on the reduced model, right? Of course, this is going to give me much better results because I avoid errors coming from the reduction, from the model reduction. Okay, so here is what I get. So I'm showing in here. So you pick up one of the points where you do the observations, right? And then you have both the real thing, because I produced it, and the observations. Now the observations are these points which just jump up and down, these purple points which just jump up and down. The observations are bad. Of course, I have noise added to them. And what you see in there, the signal itself is the red thing. And then the black cloud is the cloud of particles that follow the signal. So all the particles follow the signal, right? Of course, they are much closer to the signal than the observation itself. And you can compute the average, the estimator for the signal, a pointwise estimator for the signal at that point, and is this green dot in here. So, you know, for all of them, we get very good results. Now, nudging is so good that in fact, in itself, it can replace the tempering, this method that we had to use. So if you use the nudging properly for this particular case, for the twin experiments, it does almost as good, if not better, than applying tempering. Tempering is really very expensive, but we have to do it. But in this particular case, because we use nudging, we found out that it will give you results almost as good as tempering, although it's a lot cheaper than tempering. And I have some examples in here. I have some graphs in here which show exactly this. In fact, nudging itself is 3 times faster than any step on tempering, right? Which means that what we just applied nudging 3 times, we average over them, and we obtain something which looked very, very nice. Errors were a lot lower. Okay, so now for the tree experiment, of course, now we have to deal with 2 sets of errors. Errors coming from the particle filter itself, but also errors that come from the model reduction. And you still do good. So what I'm showing in here, this is how the particles spread out in the absence of any control, in terms of any data assimilation step. That if you do just tempering but not nudging, you get these purple things, and the blue things is when you get the nudging itself, right? So this is, most of the time you get it well, sometimes you don't. Sometimes you don't get it well, right? So this is not the effect of the nudging itself, is because of the model reduction. Okay, so now I'm going to show you, I'm going to stop here. I'm going to just show you the actual simulation. So what you'll see now, and I'll stop here, I promise. Okay. So on this side, this is the true signal, right? On this side, what you'll see, this is the ensemble mean, right? So you need to compare the ensemble mean with the true signal, right? Or for all the points, right? So they don't look back, do they? But in order to see exactly what is the difference, this is the difference between the two, right? So the black dots are the dots. The black dots are the dots where we did the observation. And of course, after we finished the experiment, we realized that perhaps we didn't put the black dots in the right place. We could have gotten better results if we put the black dots in different places where things are happening more than there. Because you can see in most of the places where we had black dots, the error is small. Error small means you see white, right? So perhaps we should have put the black dots, the observations, some on the boundary as well. Things are happening on the boundary. There's friction there. There's turbulence there, and to try and follow these things. But in general, you do not know where to put these things a priori, and we didn't want to cheat in that way. I'll stop here. Thank you very much.
Very exciting talk.
You're welcome.
Questions for Dan?
Adrian.
So why do you think the greatest error is along the boundary if you impose the Richet boundary conditions? I guess it's the same for all.
This is where the energy, I mean, you know, there's friction there. You know, it's right at the bottom is 0, but you know, the boundary layer is very active. Okay, so that's, you know, a lot of things are happening in there. You know, it's not that you have a smooth decay. You know, this is not, you know, this is not one of those nice heat equations that decays slowly. You know, it's turbulence, right? So we should have put at least some of the observations in there. You know, this is a big deal now. You know, if this had the viscosity, because in the absence of viscosity, then, you know, all bets are off. You know, boundary, you know, you have to impose a different type of boundary.
I have lots of questions, but one was about the determination of the lambdas.
Yeah.
You know? Can you just, this was just very quick.
Yeah.
And I think it's my fault because I designed the program and gave you very little time. So sorry about that. If you can
Give me 20 minutes and she has asked me questions.
No. You have time now for discussion.
Good.
I want lots of discussion on this.
Good. Go on.
So just determining the parameter lambda.
Okay.
Okay, so I understand that you have to do it, and the Xi here is really the same because you want to be able to apply Gisanov.
Yeah. So we really want to apply Gisanov. If you didn't put the Xi in here, then you have to say this lambda has to be, you know, you have to put the inverse of this thing to get it right and so on. So we didn't want to cheat. So let's just put the Xi in there, and we think of lambda as basically just some additional parameter, some amplitude that you play with it, but you still keep the Xi. And the way to think about this, you know, this Brownian motion in here, you put the Brownian motion in there, and then you say, okay, I'm going to just perturb the Brownian motion. So your perturbation is on the noise side, you know, so you perturb the noise. That's all you do. So you just say, well, my noise is now going to be, I'm not going to go in that direction. I'm going to make a small perturbation of the noise, right? So you can see now, you know, this is the thing that comes in there. It's very, very specific. You're not going to play with it. You're not going to put any term in there to hope that it's going to. It has to be very specific so that you get a transition, so that you get a distribution which is absolutely continuous with respect to the other one. Okay. Yeah.
You somehow know that your model has
well, first of all, I'm trying to make the correction so that I still keep the model on the right track, so that it still looks the right way. But
this is a model reduction from something you know the truth with.
No, the model still has the same degree, the same number of degrees of freedom, right? The only thing is, so what happens, the thing that I cannot control here is this noise, the random. So I know I toss my coin and I get the number.
This is a reduced one, right? From
Yeah, but
the high resolution.
so you're asking about this one.
Yes.
Okay, so
that's your model F.
yeah.
And you know exactly the directions where
Okay.
when directions where there are seeds. So basically you don't have any numbers.
Yeah, so the model error is done before you do anything. So the model error is done at the beginning, offline.
No, I understand that. So my question is, so your technique is going to work if you know where your model error is.
Yes, and I have to compute the size, and I have to find out the number of
Just
Brownian motions.
to think how this will apply to a climate model, because most of the time we have no idea.
Okay, so this, okay, I mean, what I can tell you is I have to calibrate my model, right? Now, to calibrate my model, what I do here is, you know, what people do in practice, and it's called reanalysis. So I have to have the results for a period of time, and I have to use those results for that period of time, right? Otherwise, I cannot calibrate the model. Otherwise, I cannot do this model reduction. Ted.
I think the question is that you're in a sort of a perfect model setup because of observation from this whole.
Well, I mean,
They're not from some other source, and then your the model error that you're dealing with is resolution.
Exactly.
I
Exactly.
think what his point is that if you're talking about observations of the real planet system, there is no calibration.
Right.
You don't have a perfect
Right.
reference point. So it's not just the resolution aspect. It's also the mismatch between your primitive equations or whatever and the real.
Right. We do not cover that here. But what I can add to what Ted just said is that disk size that do not have to be set in stone, right? So you can gradually use your new information to amend the size. But for climate models, if you want to see what happens 200 years in advance, you don't have information, of course, this is just guesswork. Oh no.
Just brings to mind what you could do here is to introduce what model error. You could use a 4-layer model as truth, and then use a 2-layer approximation to kind of make up a model error as well. But that goes a little bit in the way of making it less clean. And since you have a layer formulation, that would be very simple to do.
Okay.
It's just a suggestion.
I take this on board. I take this on board. I go back to my team of 100 people and I ask I'll ask them if we can do what you suggested. Is okay.
4 layers to 2, and in your paper, I'm reading your paper, it starts with the n layer. Okay, so take n is 4 and do your dA for n is 2. Then your
okay.
is happy, and then
So
everybody is happy with that.
I'm not sure if he's going to be happy because this is. Joachim, I didn't answer your question in the end, but go on.
No, we can discuss this later. Just make sure that when you write this paper with Ono together, mention the Newton Institute.
Of course, that's for sure. I will definitely do that. Yeah. So just to yeah. Okay. Go on.
There is a question online.
Okay.
From Marianne there. Have you tried reducing the model even further? Was there a specific reason for choosing the model reduction?
Yes. So I think we try to reduce the model further. If you reduce the model further, disk size are going to be different and in amplitude bigger because the errors are going to be higher. We stopped at this level because this was the one that was we could handle with the workstation. Right, so we use a workstation, and with the workstation, we wanted to have just the 100 particles, and it was, coarse enough so that we could use this, and we didn't need to make it more coarser than that. But yes, you can do it for a coarser thing, and obviously, the results are not going to be just as good. And I think in the paper we have some sort of description of what you miss out, but you have to look at the previous paper where you look at the uncertainty quantification, not the data assimilation paper. Tobias.
I mean, so I didn't get how you get the lambda. You just minimize 9 or.
Okay, so Joachim asked me the same question, so I didn't get to answer him the question. So I have to minimize 9, right? Then that means I have to maximize what's inside, right? You go and maximize what's inside. Sorry, no, I have to maximize 9, which means that because it has to be as close as to 1, which means I have to minimize what's inside, right? And then in here, right, you write everything neatly. So the first thing what you do, you have to take the expected value of this respect to fn minus 1, ftn minus 1. Why is that? Because in the Gisanov, you have to have things that are measurable with respect to the right space. You shouldn't so you have to get rid of this delta WT by taking conditional expectation. You take conditional expectation on that thing, and then the result is going to be what complicated formula you saw there is just a quadratic function in lambda. So just minimize the quadratic function. It's as simple as that.
How did you get Q of lambda? Maybe this is too much. I mean, maybe we have to discuss this later.
It's just computed. It's coming from here. It's sort of, you just take lambda is, you just take expected value of this thing, and you just get the formula. You look in the paper. Everything is explicit. Everything is explicit. There's no hanky-panky. There's no, I don't know, any gradient descent method, nothing. It's just explicit as a quadratic formula in lambda, multidimensional, because I have to have one lambda per each source of noise. And we have 50 sources of noise, I think, here. But, you know, you just get it. No.
So could this nudging be considered kind of playing a similar role to inflation and in Kalman filters and moving your particles closer to
Okay.
the observation?
Excellent question. So this is what we are trying to do now. This doesn't inflate, this keeps, so it would be inflation if you put something in here, in front of the noise. This is in the drift part. So this is just shifts a little bit the noise to the right, to the left, that sort of things. But what we're trying to do now, we're trying to explain inflation, right? Which means we put a mu in here and try to we try to obtain the optimal mu in there. This is much, much harder because you fundamentally change the whole law of the signal. But at the level of the discrete case, not continuous case, because in continuous case it's not going to go, they're not absolutely continuous with respect to each other. You can still compute the Radon-Nikodny derivatives and so on, and you can still perform that. What do you think we end up with? The results that we end up with is that your inflation must be very, very small. So you can do slightly better, but the inflation must be very, very small, of order 10 to the power -4, right? So you can go, so rather than having 1, you can go up or down by 10 to the power -4. But maybe we just got the wrong model, maybe we have to, but we have something in that direction to try to explain inflation by using nudging.
So my understanding, the nudging moving position of the particles, I would call that data assimilation. So
Sorry?
the data assimilation is basically moving your first guess trajectory to be near the observation. So I would say that your nudging is a form of data assimilation.
The whole thing is data assimilation. I'm trying to convince everybody I'm doing data assimilation here. Trust me, this is what I'm doing.
It's the idea that you end up with all the particles having roughly equal probability.
No, so this is, you can never get to that thing because, you know, your optimization takes into account where the particle lands, intuitively, the prediction step, what you do is say, well, I have this prediction step, I have the forecast, but I'm only doing the forecast based on the new data. And I'm trying to maximize these likelihood functions in there, right? But, you know, I can never get them to be all equal to 1, right? Because of all these constraints that you have in there, right? But they get better. They get, you know, the likelihood functions get higher for each one of them. But it's not like at the end of the nudging, all the particles have likelihoods equal to 1. This is not on the par with what Peter Yan is doing. It's not. Okay. Yes.
So my question, I have the equation 8,
Yeah.
which is your nudging equation. I'm guessing, as I understand it, constructed it in such a way that it is equivalent in distribution, right? To
The one without the nudging.
right?
Yeah.
Okay. Now, okay, very good. But now this lambda k that you constructed, how does it impact the data? This is what it should be, right?
Excellent point. Okay, so I'm sorry I missed this. So when you go and, you know, the data is in here. This is why. Why is the data, right? So why is in there? So in the actual function that gives you the lambda, they depend on y. So the lambdas will depend on y.
So what is this?
This one.
Yeah, what is
Okay, so you have to take what's inside here.
okay, this is to make it like this is the Crisan.
Yeah. You have to make what's inside here you compute the conditional expectation of this with respect to ftn minus 1, compute all of this, y stays put, is fixed. You embed the data in there, right? And then you obtain a function, which we call q, of lambda and x and y, which you minimize. So the minimizer lambda will depend on y.
But actually what I don't understand is this 10 or this 11. Why do you choose it?
Oh, okay.
I'm slow, maybe.
Okay, so the likelihoods are given by this exponential.
I understand that the 10 is blue.
Yeah.
The 10 in black, but I don't understand. What is
Okay. So this is the old likelihood. Then the new likelihood is the old likelihood multiplied by the Radon-Nikodym derivative of the coming from the Dirsanov. I still have to use the old likelihood in there. It's the likelihood.
Sorry, I missed that point. Of course, it's obvious.
So it's not just, I don't just minimize respect to the Radon-Nikodym derivative. I have to take into account the old likelihood.
I think this is a good time to stop for the questions. I think there's going to be a lot more in the discussion and the
Okay.
coffee break. Let's thank Dan again for this wonderful talk.
Thank you. Okay, now I see 14 questions on. Okay, so these are not for me. Okay, thank you.
So we reconvene at 11:15, if that's okay. We have a buffer zone.